Hey everyone, welcome to another session together. It is day 1 of Unit 10, and we are going to learn about solutions today. As it notes, if you haven't already done so, please go back and watch the Zoom meeting from today. It'll just give you some setup, some reference, so that this just doesn't seem kind of out of nowhere. All right. The focus today, like I mentioned about solutions, is to define some terms and then also to define some concentration units. Please set up your EQ at the top of your notes. That gives you a guide for what you should know by the time we're done. It helps you write your summary and just gives you kind of some focus for today. So solution terms and concentration units. Let's get into it. Let's start with some of the vocab that we use pretty often when we're talking about solutions. The one word is the solute. This is the thing that is getting dissolved or mixed in to something else. It's the thing you have less of. So because it has to get covered up by the other part, you have to have less of it so that there's enough of everything else to cover up the solute. The solvent then is what is doing the dissolving. So you're mixing the solute into the solvent. The solvent particles then are covering up the solute in a way so that we don't see it anymore. You can only have one solvent because it's whatever you have that is the most. So you obviously can only have one thing that is the highest amount, and then anything else would be considered the solute. Even if there's a lot of different things, they would all still be solutes, and then you'd have one solvent. Here's a great example. Shampoos have lots and lots of things mixed together. The things that make it smell good, the things that make your hair shiny, the things that clean your hair, the things that keep it from decomposing. There's lots of things that they mix into water. Water is the most common ingredient in this particular shampoo. So then water becomes the solvent, and then everything else is considered a solute. Because in this example, the bonding of all of these things must be similar enough to water that water is able to be attracted to it, cover it up, and create what we think of as a solution. All of these things mixed together to create that shampoo. So then when you combine a solute and a solvent, that is when you get your solution. And possibly you remember way back to Unit 1 in Pre-AP Chem A, this is also known as a homogeneous mixture. So remember, it's a mixture because all of the particles in it are not chemically combined. They are just mixed together. Homogeneous because it all looks the same. They all, like you don't see the different solute particles separate from each other or separate from the solvent. Everything is mixed together. Homogeneous mixture. All right, so here's some examples of things in your world, common things, and I'm just giving you the little trivia question. Can you spot the non-solution? So think about what these things would be made of. Let's see. Okay, so think about ice cream. It's got probably some cream and sugar. This must have some cherries and chocolate in it. This is an IV drip that is basically sodium chloride, but then it tells you that it's got some other stuff in it because it says it's only 0.9% sodium chloride. And then it probably has some other things in it that give nutrients to whoever needs it. And then you've got cold brew, so coffee drink. So again, this probably has some water, some flavors, those kinds of things. And then Tylenol, which is really acetaminophen. Okay, so from that description, can you spot it? Yep, ding, ding, ding. The Tylenol, which is just called acetaminophen, would be a compound. So if this is a compound, all the others would be solutions. So this is your non-solution. Okay, a couple more vocab words I want you to be familiar with. If you have something that is called saturated, this is a way we describe solutions. Think of like a saturated market, meaning that there's the same thing in so many different stores that like pretty much no one's making money off of that thing anymore. It's just too common. Or think of it as a saturated sponge. If you have a sponge that is saturated and then you used that sponge to try to wipe up something, there's so much water soaked into that sponge that you wouldn't be able to fit any more liquid or water. So a saturated solution is a solution that is so full of solute that no more solvent can cover up the solute if more was added. So think of it that way. So it's the maximum amount of solute that can be dissolved at a certain temperature. We'll talk more about how temperature affects solutions later, but for now, just know that if you have a certain temperature, there's a certain amount of stuff that can dissolve into your solvent. And if it's totally full, like no more solvent can cover up anything else, that's saturated. An unsaturated solution, think about what the prefix un does. So it means now it's not the maximum amount, right? So it's less than the maximum amount. So if you have a solution, it's got something in it, it means that there's some solvent that's not dissolving anything. It's just floating around. Some solute is dissolved, but not the maximum amount. And then you have something called supersaturated. So think of like something that's supersized or Superman. They're more than normal. So a supersaturated solution actually contains more than the maximum amount that can be dissolved at that temperature. And this is a tricky thing because it sounds weird to be like, well, wait a second, how can you get more than the max? It's because you didn't keep it at that same temperature the whole time. You heated it up, which gave the solvent more energy, and then you dissolved more. Then you cooled it back down to that temperature, that original temperature, and that all that stuff stayed dissolved because it was already dissolved. That becomes a supersaturated solution. All of these have the same word, solution, 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 which should be a homogeneous mixture. So then how will you know the difference between them? Well, this brings us back to that demo that I did for our day 1 Zoom meeting. So the idea here is that demo had 3 different flasks, that one of them was saturated, one was unsaturated, and one was supersaturated. So think about what I did and then notice that I got different results. What did I do in that demo? That's right, I added more solute. So if I add more solute and it is able to dissolve, that must have meant that I had an unsaturated solution, because remember, unsaturated has less than the maximum amount. So in that case, if it was already unsaturated and I add more, it can still dissolve. There's still solvent available to cover up the solute. If I add more and it does not dissolve, so this was the first flask that I did where you could see like some of those crystals were gathering at the bottom. They weren't dissolving. They were just kind of floating around. Well, that was because that flask was a saturated solution. It already had the maximum amount that could be dissolved, and I didn't change the temperature. It just stayed at room temperature. So because of that, when I added more, it just sunk to the bottom because the extra solute could not be dissolved. And then the last demo that I did, the last flask, was that really interesting one where it actually came out of solution. Well, that was that supersaturated idea. So because there was so much packed in there, when I added more, there was no place for those particles to roll around like a liquid. So they had to be a solid. They came out of solution and created a solid, but they didn't freeze. Remember, they released energy and it actually got hot because you just took something that was a liquid that was so full that it can't be a liquid anymore. It had to instead be a solid. So those are some of the vocab terms of how we describe things about solutions: saturated, unsaturated, supersaturated, solute, solvent, homogeneous mixture, those kinds of things. Go ahead and do a level 1 question so far, something that would just review one or more of those terms we've done so far. All right, a couple other vocab words I want you to know that are related to describing solutions. One of them is a non-electrolyte. Well, we of course know that non means it doesn't, and then electrolyte kind of sounds like electricity or electron. And so a non-electrolyte is something that does not conduct electricity. Okay, so this is a little bit of a link to our last unit. If it doesn't conduct electricity, that means that probably you have molecules that are dissolved as your solute. And so instead of those particles breaking up into positive and negative pieces, they dissolve as full molecules. Okay, so now think back to our last unit, day 1, with that light bulb demo. So when I dissolved sugar in water, I created a solution. But the sugar was just dissolved as full molecules, no positive or negative pieces. So there was no place for the electrons from the electricity to be attracted. And so it didn't conduct electricity. So that's a non-electrolyte. An electrolyte solution is all the opposite. It will conduct electricity. So probably we're not dissolving as molecules. Instead, we're talking about ionic compounds. So your solute is some type of ionic compound, but then when that ionic compound dissolves, it now splits up into positive pieces and negative pieces. And since there's free moving positive pieces, that electricity that is negative particles can be attracted to the positive ions, and those are spread out all the way through the solution so that it can conduct electricity. So this is why Gatorade does conduct electricity. There are electrolytes put in there on purpose because that's what you're getting out of your body when you sweat a lot. And remember, that was what Gatorade was marketed towards, was athletes, specifically people that are working really hard and sweating a lot, to replace those electrolytes that you've gotten rid of. So it is an actual real thing. The ionic compound that they put in there doesn't really have a salty taste because of all the other things that are in the Gatorade. So you don't necessarily taste salt the way you would like if you put sodium chloride in there, but that would actually achieve the same purpose. Maybe it wouldn't taste as good though. But that is why Gatorade does conduct electricity. So there's a couple more vocab terms related to solution. The other part of what I want to talk about today is how do we calculate concentration. So first of all, we need to talk about what concentration is. It's something related to solution, but really what it's talking about is the amount of solute that you have dissolved in some amount of solvent to make a solution. So what we're going to do then is, so that's another way to describe a solution. So, things like saturated, unsaturated, non-electrolyte, concentrated or not concentrated. These are all words that we can use to describe something about that solution. So for the second part, or really the third part, I guess, of our notes today, I want to show you a couple very common ways to calculate concentration. First, though, go ahead and do a level 2 question. You could do a compare contrast. You could draw a picture. Something like that. Okay, so then now I want to show you how to calculate concentration. So we have a couple options. One of them is called molality, and the symbol is little m. And it's called molality because what it's focusing on is the number of moles of solute. So whatever you're mixing in, how many moles of that did you put in there? And remember, the symbol is little m. So little m is the number of moles of solute over, wait a second, moles. Well, if moles are being used again, guess what else we will have? Okay, why is Avogadro so thin? You're right. It's because he's malnourished. Poor guy. I feel bad for him. Okay. Anyway, back to molality. So it's the number of moles of solute. So like we might measure out grams and we can turn that into moles. But then for the bottom of molality, you need the kilograms of solvent. So it could be like, how many grams of sugar did you put in how many grams of water? We could turn grams of sugar into moles of solute, and we could turn grams of water into kilograms of solvent, divide them to get your answer. So that's what molality is, which is a pretty common way to measure something about your solution, your concentration. The other one we're going to use is molarity. And yes, they are very similar. Just be careful. Molarity is capital M. And it's still moles of solute on top. So moles of solute would be consistent. But the difference with molarity compared to molality, molarity is liters of solution on the bottom. So don't get confused. Solution is solute plus solvent, and it's measured in volume. Molality is just the solvent on the bottom, and it's measured in mass, specifically kilograms. All right, so here's an example of moles per liter. 2 moles per liter. Okay, so then now instead of just thinking or describing a solution, you can actually measure and give a quantitative description of a solution, thinking about things like solute and solvent and solution. All right, go ahead and do a level 3 question and a summary, but don't stop the video yet because I'm actually going to do a couple example calculations, but those will go on your output page. So go ahead and finish off your notes. Level 3 question. You can do a summary later maybe. Okay. Let's go ahead and do a couple examples of how we might use molality and molarity for something more practical. So here's the first example. What if I asked you for the molality of a solution that is 5 grams of potassium nitrate and 96 grams of water? Okay, well, we see that this is the higher number, so that means that this has to be the solvent. This is the lower number, so that has to be the solute. So there's some information we already know. Well, let's think about what we want. So let's figure out how to solve problems like this. We want molality, but remember, molality is moles of solute, kilograms of solvent. So this is what I need to have. I need to have moles of solute and kilograms of solvent. Okay, well, what do we have? We have grams of solute. Well, I know that I can turn grams into moles, so I'll be able to do that. And I have grams of solvent. Well, if I have grams of solvent, I can get that to kilograms of solvent. So we got this. All right, let's work through it. Here we go. So you remember, or I'll remind you, that you look at the periodic table and you add up the molar masses of whatever's in your compound to get the number of grams in 1 mole. Because remember, we're trying to get to moles of solute and I have grams of solute. So if I add this up, I get 101.17 grams per mole. So that is my conversion between grams and moles. I'm starting with grams, so that means that in my brackets, this is DA conversion stuff, I want to get rid of grams. So that means that the grams will go on the bottom, so it cancels, and the moles will be on top. So now grams is going to go away. If I take 5.0 divided by 101.17 times 1, I get 0.04942. I'm not worried about sig figs yet because this isn't my final answer, but it's moles of KNO3. All right, remember, I'm looking for molality, which is moles over kilograms. I already got my moles. Now I'm going to take my 96 grams of water, and you can maybe do this in your head, but sometimes people make mistakes about, wait, is it times 1,000 or divided by 1,000? If you set up your DA, you're less likely to make that mistake. There's 1,000 grams in 1 kilogram. So if I divide by 1,000 grams, I'll get 0.0960 kilograms of water. Okay, so then now I'm ready to solve my problem because remember, I wanted molality, which is moles of solute over kilograms of solvent. Moles of solute I have right there. Kilograms of solvent I have right there. So I take this number of moles of solute divided by this number of kilograms of solvent. When I get my answer, now I have to pay attention to sig figs. This has 3, this has 2. So whatever you get on your calculator, round it off to 2 sig figs, 0.51 molality. And we're going to learn later this unit of something you would use molality for, because right now it seems kind of random unless you're a chemist making some type of solution, but molality affects different things. One of them we're going to talk about is related to like boiling point and freezing point. So we'll come back to this later. For now, this is just kind of an intro day, how to calculate something called molality. All right? Okay, let's do another one. How about this? Find the amount of grams of silver nitrate needed to make 375 milliliters of a 0.75 molarity solution. Okay, now this could be a very normal thing. I could be a lab prep person or a teacher or a lab TA, and I know that whatever lab I'm doing with my students, I need to have 375 milliliters, and that will be enough for the whole group. But I also know that I need to have a 0.75 molarity solution. So that's what I'm supposed to make. So how many grams of silver nitrate will I need if that's what my goal is? Okay, well, let's do that same thing. What do we actually want? Grams of solute is what we want. What do we have? Well, we have milliliters of solution, okay? We have molarity. Well, remember that molarity is moles of solute and liters of solution. So let's try to make a plan here. I don't want liters of solution, but that means I could cancel it from milliliters of solution. And then I don't want moles, I want grams. But I could look up the molar mass, which would cancel moles and get me to grams. So this is a DA problem. We can do this. All right, let's do it together. Here we go. Do this problem with me. You're on an output page still. Okay. My given that I'm going to start with is 375 milliliters of solution. And the reason I'm starting with this given instead of this one is because really remember, capital M is something over something. So that's a conversion. So this is just your standalone given. But remember, capital M is moles per liter. So I can't just keep the milliliter. So my first conversion is going from liters to milliliters. Or sorry, milliliters to liters. So milliliters cancels, I'm at liters. Now I can use molarity, and liters will automatically be on the bottom because that's the definition of molarity. And then 0.750 moles of solute will be on top. So remember, the definition of molarity is moles per liter. Well, anytime you have per something like miles per hour or meters per second or moles per liter, the per is for 1. So 0.75 moles of solute over 1 liter is the same as 0.750 molarity. So now milliliters is gone, liters is gone, I'm at moles, but remember I was trying to get to grams. So that means we need to again add up the molar mass, but this time for silver nitrate. So silver from the periodic table to 2 decimal places, nitrogen to 2 decimal places, oxygen to 2 decimal places times 3. Add all of that up, I get 169.94 grams per mole. Well, mole is what I want to cancel, so that's going to go on the bottom, grams on top. So now moles of solute cancels. I'm with grams of solute, which is what the problem was asking for. I multiply all the numbers on the top, divide all the numbers on the bottom. It looks like I can keep 1, 2, 3 sig figs, 1, 2, 3 sig figs. So whatever you get on your calculator, round it off to 3 sig figs. So 47.8 grams of solute. So another application of that molarity concentration. Okay, let's try one more example together to just kind of step up our game. What if we were given molarity and I want to find molality instead? Okay, here we go. So what do we want? We want molality. But remember, to find molality, that means we need moles of solute and kilograms of solvent. So that's really what I need. So what I have is molarity, but remember, molarity is moles of solute. See how that already matches? But what I have is liters of solution, and I want kilograms of solvent. That's going to be a problem. But I do also have this density thing. Why might that be useful? Well, that's grams in solution and milliliters of solution. Okay, so then that might help me for part of this. So that's where we're going. So this takes a little bit more thinking, but if we hang in there together, we can do this. So let's try this one out. So here we go. This is what I have. 9.1 molarity really equals 9.1 moles of solute over 1 liter of solution. That's what this means. What I need is molality. So molality is still moles of solute. So I already have that. But what I don't have is kilograms of solvent. So this really should be like an X here. This is what I'm trying to find. But the problem is that is solution and that is solvent. Well, the solution is made from the solute plus the solvent. We talked about that in our vocab today. So if I'm trying to find the solvent, I need to take my solution minus my solute to get my solvent. So now take a look at the stuff we have. I need grams of solution, but I have liters of solution. I want grams of solute, but I have moles of solute. Well, I can figure this out. I can take liters, which is volume, and turn it into grams, which is mass, because think about that. The relationship between mass and volume, what is that again? Yeah, it's density. So if I have liters of solution, I can use density to get from volume to grams, so then I'll have grams of solution. And because I have moles, I know that I can get from moles to grams. So 2 separate problems, but I can do this. So here we go. I'm going to start with my 1 liter of solution that I have, and I'm going to try to get it into mass. But the density units are milliliters. So first I'm going to have to go from liters to milliliters. So now liters is gone, I'm at milliliters. Then I can use density, and remember, anytime there's per milliliters, there's really a 1 implied there. So in 1 milliliters of solution, there's 1.062 grams in that solution. So milliliters goes away, I'm left with grams. So now I've got 1,062 grams of solution. Based on the density, I turned volume into grams. So now I've got this number. But now I have to get grams of solute. I take my moles of solute, and HCl was our solute because it says it's a solution of HCl. And then I'm going to add up the molar mass. So I look at the periodic table. Hydrogen is 1.01. Chlorine is 35.45. Add it together. So 36.46 grams of HCl for every 1 mole. Mole goes away. I'm left with grams. This will be my grams of solute. And I wasn't worried about sig figs yet because this wasn't a final answer. Okay, now the reason we found these 2 pieces of information is because remember, we're trying to find molality, which just focuses on the solvent. So back to this, if I subtract the solute from your solution, you'll be left with the solvent. So the 1,062 grams of solution minus the 332 grams of solute gives me 730 grams of solvent. All right, so then now I'm ready to go back up here. I can't use grams, but I know that there's 1,000 grams in 1 kilogram, so I need to divide by 1,000. So then that will give me from grams to kilograms. This stays the same, 9.1 moles of solute from the given divided by 0.730 kilograms of solvent. And again, don't let that confuse you. I just did that step kind of in my head. So 730 grams of solvent divided by 1,000 grams times 1 kilogram gets me to kilograms. Divide that out. Now we got to focus on sig figs. Look back at your givens. This has 2. This has 1, 2, 3, 4. I can't be more specific than my smallest measurement. So you get this on your calculator, round it off. 2 sig figs, 12 molality. So this takes you through lots of different chemistry steps to show you what you know. It shows you know the definitions of molality and molarity. It shows that you know the definition of solution. It shows that you know how density works. It shows you know how molar mass works. So all of that cool stuff coming together to answer a question. Yeah, this is a very specific chemistry question. I get that. But it is something that is super useful to chemists. All right. So after those vocab terms and examples, that is the end of our first day of Unit 10. So here's the things that I'd like you to do before our next session. If you've not already done so, make your Unit 10 Notability folder and put the Unit 10 plan into Notability. So you have that as a reference. If you didn't already do so, finish your COSTA questions and your summary from today's notes. And then there is a solutions practice assignment. It's 2 pages. The first page looks like some of the calculations we just did as examples. The second page goes with the day 2 notes. So don't worry about them. You probably could figure it out, but there's no reason to. Just do the first page. And then if you feel like you want more practice or feel like you need it, there are some unit practice problems from today. They're posted on the unit plan that you could look at. And that's it. That's the end of our day 1. We'll see you at our next Zoom meeting. Thanks so much for joining in. Bye.